Hi, this is an AP Chemistry video. We're going to be covering topic 3.7, which is solutions and mixtures. So a solution is a physical combination of any state of matter in which the macroscopic properties don't vary. So a solution could be, our air is different gases dissolved in one another, nitrogen and oxygen primarily. It could be a carbonated beverage with gas dissolved in waters, essentially. It could be a liquid dissolved in a liquid, like vinegar is acetic acid in water. But most of the solutions that we're dealing with in chemistry are going to be a solid solute dissolved in usually water. So we know that solutions are really homogeneous mixtures. Mixtures are just any two or more pure substances mixed together, but uniform composition. Heterogeneous mixtures are not uniform throughout, so if you were to sample a different area in the heterogeneous, you might get a substance that has different properties. So we're focusing on homogeneous mixtures, which are solutions. So you can kind of see in my diagram here, uniform throughout versus here. If I were to take a sample at the top, it's going to be different than a sample at the bottom. This is just showing you solvation at a macroscopic level. You always have a solvent. Usually it's water. Water is the universal solvent, a solute, and then you make that solution, which again is homogeneous or homogeneous. Quantitatively, we can describe solutions in many different ways. Molarity is one of the most common ways in chemistry. This is moles of solute over liters of the entire solution, and we will be using this quite a bit. We are also going to be doing dilutions, so we are going to have a stock solution that's more concentrated. We're going to take a certain volume of that stock solution, and then we're going to have a desired molarity that we're trying to make. And we're going to have a desired amount of that molarity, which is the volume of dilution. We're going to be using pipettes, so our lab that we're going to do in this unit will be using pipettes to transfer. And it's just a way to measure and transfer volumes precisely. So in terms of preparing a solution, this is something you're going to do in the lab. You're going to use a pipette to draw up a certain amount of the stock solution, add it to another volumetric flask or a test tube, and then you're going to add water. In this case, it's a volumetric flask, so you just add water to the line. In our lab, we're going to be pipetting a certain amount of water into a test tube so we know that we have exactly 10 mils. So for example, if I have 2 mils of my stock solution and I want a 10 mil solution, I would add 8 more mils. And I'll do that with the pipette to be exact, of distilled or deionized water. Another way to make solutions is to take a solid, and again, they're showing you the volumetric flask. It's a good way to make solutions. It's a precise piece of instrument. And what you do is you would mass out the solid that you would need based on the molarity, which is really then based on the moles of the solute that you want. And then you would add enough water, again, depending on the size of the volumetric flask. So this is another thing I want to talk about. Solutions. When something goes into solutions, sometimes it's an electrolyte. It'll conduct electricity. We're going to focus right now on strong electrolytes, which are typically ionic compounds, strong acids, and strong bases. Weak electrolytes are things that partially dissolve and give ions. So weak acids do this, and weak bases are weak electrolytes. And then non-electrolytes are substances that don't dissociate into ions at all, such as sugar and oil and alcohol. So when we do think about a strong electrolyte, we want to be able to think about what it's doing in water. So breaking an electrolyte apart, like if I have solid aluminum chloride, when I put it in water, it's going to break into aluminum ions, and those are aqueous now, and chloride ions, which are also aqueous, and we want to show that there's 3 of them. A common misconception here is to think that I need to have a 2 down there because chlorine is diatomic. That is not true for the ion. That's only for the gas. So you want to show that there are 3 separate ions of chloride and 1 ion of aluminum for every 1 formula unit of aluminum chloride. One more example here. So this is a ionic compound, and we can assume it's soluble in water, and we'll talk about that a little bit more in another topic. And we do have a polyatomic ion. So in this case, you do want to keep that polyatomic ion together. So when this breaks apart, we're going to get sodium ions in water, and we have 3 of them, 3 separate ions. So you want to think of it like this. Plus, we're going to have that phosphate ion, and that's going to stay together and only be 1 ion. Just to reference your polyatomic ion sheet, we'll talk about this more when we get to the acid-base unit, but for now, there's still some questions where I will ask you if it's a strong electrolyte or not. In AP chemistry, there's 5 strong acids that all dissociate 100%. So all of these are going to be strong electrolytes. So, hydrochloric acid is going to break up into 100% into hydrogen and chloride ions. And what you need to do is, just realize that if it's an acid, for us right now, an acid is something that starts with a hydrogen ion. That isn't totally true, but for what we do, it will be for now. If it's an acid and it's not one of these 5, that means it's a weak acid, and that means it's a weak electrolyte. So if we try this question here, which of these 3 solutions will conduct electricity the best? What you want to do is evaluate the substance. They're all the same molarity. This is an acid, but it's not one of the 5. This is acetic acid, so it's a weak acid. So that means it's a weak electrolyte. This is an alcohol. It's molecular. It's not ionic. It's all nonmetals. And so that is also going to be a non-electrolyte or a weak electrolyte. This is the one that's going to be conduct electricity the best. Potassium iodide is a ionic compound that will break up into ions, and these are the ions that move and allow it to conduct electricity when it's in 2 different solutions with different molarities. And sometimes you'll want to know what is the total sodium ion, in this case, concentration. So we have 2 different compounds, sodium carbonate, that would dissociate and give us 2 moles of sodium for every 1 mole of carbonate. And we have sodium bicarbonate, which is going to give us 1 mole of sodium for every 1 mole of the formula unit of the compound. So if I start with my 56 milliliters of sodium carbonate and I convert this to liters, I'm in liters then of sodium carbonate. Now I'm going to use that molarity again, 1.4 moles of sodium bicarbonate for every 1 liter of sodium bicarbonate. And now I'm interested in the sodium ion, so I'm going to do that ion ratio to formula unit. So there's 2 moles of sodium ions for every 1 mole of the sodium carbonate. When I do this, I get 0.157 moles of sodium ions just from that solution. So I'm going to try to make this smaller. Similar, I'm going to do the sodium bicarbonate, starting with the 20.5 milliliters. I'm going to convert that to liter. I'm going to use the given molarity, 2.3. There's that many moles of sodium bicarbonate in 1 liter. And then 1 mole of sodium ion for every 1 mole of sodium bicarbonate. And that will give me 0.0472, can't write, 0.0472 moles of sodium ions. So ultimately what I'm doing here is I'm trying to get the molarity of the sodium ions. So I need to know the moles of sodium ions over the volume in liters of the solution. So I am going to I'm going to move this over. I'm going to take my moles I just calculated, my 0.157 plus 0.0472. Those are my moles of sodium ions. So my total moles of sodium in this solution divided by the total volume of the solution, converted my milliliters to liters. And when I do that, I get 2.7 moles per liter of sodium ions. And you can also represent that as 2.7 capital M. One more example. Actually, a couple more examples. I'm kind of going out of order. So here, if a 200 milliliters of a 0.60 molar magnesium chloride is added to 400 mils of water, what's the concentration of the magnesium ions? So for this question, I know that my volume total, so they say the volumes are additive, means that I have 200 mils and 400 mils. So really I have 600 mils of solution here. And that 600 mils is the same as 0.600 liters. In terms of the magnesium chloride, I have 200 mils of magnesium chloride, but I'm going to convert that into liter. I'm going to use the molarity as a conversion. So 0.60 moles of magnesium chloride for every 1 liter of magnesium chloride. Now I'm going to focus in on the chloride. Oops, am I doing the chloride? What is the constant? Oops, I should do the magnesium. The magnesium, you could do the chloride. So there's 1 mole of magnesium ions for every 1 mole of magnesium chloride. That'll give me my moles, and then I'm going to divide that by that volume. So when I do this, I'm going to do it with you now because I don't have it worked out. 200 divided by 1,000 times 0.6 times 1. So I end up with 0.12 moles of magnesium ions. So to calculate the molarity of the magnesium ion, it's going to be 0.12 moles over that total volume. And when I do that, this is 0.120 sig figs, I get 0.200 molarity of magnesium ions. So my answer here is going to be A. Here's another problem. So approximately what mass of copper 2-sulfate pentahydrate is required to prepare 250 mils of 0.1 molar copper 2-sulfate solution? So when I do this problem, I am going to start with my volume. This time I'm just going to convert it to liter in my head. I'm going to use that molarity to figure out how many moles of copper 2-sulfate pentahydrate I have. And then I'm going to use the molar mass of that compound. So 250 grams per mole. And that gives me 6.25 grams of copper 2-sulfate pentahydrate that I would need in order to create a 0.1 molar solution. So my correct answer there is going to be B. Okay, let's do another problem here. If the concentration of silver ions in a saturated solution of silver bromide is, so now we know the molarity of the silver bromide is the same as the molarity of the silver ions, because they're in a 1-to-1 mole ratio, is 7.1 to the negative 7th moles per liter. Calculate the minimum volume of distilled water in liters necessary to dissolve a 5-gram sample. So what I would want to do is start with my 5 grams of silver bromide, convert that into moles of silver bromide by using that molar mass. So 0.0266 moles of silver bromide are going to be dissolved, and I want this molarity. So I'm going to sub into the molarity equation, and I'm solving for volume. So if I sub in my molarity, and that's moles per liter, equals my moles, and my volume is my X. Once I rearrange that, volume's going to equal the moles divided by the molarity. And you can see the moles cancel, and you end up with 1 over liter, which is liter. And when you do this, you get a large number, 37,465 about. But with 2 sig figs in scientific notation, you would get 3.7 10 to the 4th liters. You don't have to put it in scientific. You could have left it with 2 sigs at 3,700, or can't write it. You would write it like this. Sorry, I can't say it. So 1, 2, 3, 4, 37,000. All right, let's do another problem here. I already did this one, didn't we? Let's do this one. This is our last problem. So here is a problem that we are preparing a mixture with 50 mils of toluene and 125 mils of benzene. We're going to assume toluene is the solute. It's in a smaller amount. That benzene is the solvent. And these are going to add together in volume. So if I have 50 mils of the toluene and 125 mils of the benzene, I'm going to have a total of 175 milliliters of solution. So first thing they want to know is the percent by mass. And percent mass is the mass of the solute over the mass of the whole solution. So in order to do that, we need to have the mass of the toluene and the mass of the benzene. What we're going to do is use density. So if I have 50 mils of toluene, and I'm just going to make a kind of a heading here, so I don't have to keep writing it out, I'm going to use the density that's given, 0.867 grams per cubic centimeter. A cubic centimeter is a milliliter, so those are the same thing. So you can see that I have 43.4 grams of toluene. And I'm going to do the benzene over here, kind of make it into a kind of like a T-chart, but I might run out of room. So I have 125 milliliters, and the density is given. So this milliliter, centimeter cubed and a milliliter are the same thing. So I have 109 grams of benzene. So to calculate the percent by mass of the toluene, I'm going to take the grams of the toluene divided by the total grams of the solution, which is the toluene and the benzene, and then multiply by 100. And when I do that, I get 28.5%. I'm going to add another page here. Next, so I did the mass percent. Now I'm going to do the mole fraction. So in order to do the mole fraction, I need to know the moles of the toluene and the benzene. So I'm going to do that calculation right now. So I know that I have 43.4 grams of toluene, and up above in the question, I gave you the molar mass. So I have 0.471 moles of the toluene. Similarly, I'm going to take the benzene amount of grams, and I gave the molar mass up above, and I'm going to get my moles of the benzene. So my mole fraction of the toluene is going to equal the moles of the toluene over the total moles, which are both of them added together. And when I do that, I get 0.252. So that is the mole fraction for the toluene. Next, they want to know molality. Molality is moles solute over kilograms of solvent. So this is a little different than molarity. It's mass, not volume, and it's the solvent, not the whole solution. So in this question, I've already got my moles of toluene, which is 0.471. And I know my grams of benzene, my solvent, is 109 grams, which would be 0.109 kilogram. So when I do this, I end up with 4.32 moles per kilogram. A mole per kilogram, you can also write that as small m for molality. Lastly, we want to get molarity, and molarity is moles solute over the liters of the solution. So my moles of toluene is 0.471 still, and my liters of solution is adding up those milliliters up above. And when I do this, I get 2.69 moles per liter. Also, I could write that as 2.69 capital M.